And on second days, this one is the first session. Is going to deliver by Dr. Manas Das. Dr. Manas Das has been a professor in Department of Mechanical Engineering in Indian Institute of Technology, Guwahati since July 2024. He joined the department in 2012. He received his bachelor degree from the Production Engineering Department, Jadavpur University, and his master's and PhD degree from the Mechanical Engineering Department, IIT Kanpur. His research area includes advanced manufacturing, advanced finishing and micro machining processes, as well as additive manufacturing. He has published more than 115 publications in international journals and 82 international conferences. He has a 19 patent in his credit. He has also written a 31 book chapters and one book on surface finishing. He has guided 12 PhDs and presently he is supervising 6 PhD students in his broad manufacturing area. Now with this short biography of Dr. Manas Das, I request to Professor Manas Das to take over the session. Professor Manas Das, please.
Thank you, Professor Taylor, for giving me a nice introduction. So,
Thank you very much, sir.
So I work in the actual area of micro machining process. So I started my work with a nano finishing process, basically using magnetorheological finishing, magnetorheological abrasive flow finishing process, and then rotational magnetorheological abrasive flow finishing process. So uh, after that, actually, I started working here initially with the finishing area, and after that, I started working on electrochemical machining process, mostly actually in the micro machining domain, and then micro electro discharge machining process. And nowadays, I am also working in additive manufacturing process. So here, actually, we have developed directed energy deposition, one customized experimental setup of additive manufacturing we have developed for metal additive manufacturing process. So, other things actually we are doing plasma polishing. So this plasma polishing we are using helium and oxygen gas, and using SF6 we are actually polishing some brittle materials like quartz, glass. So when these actually brittle materials, there are some micro cracks are there. So these cracks actually it is removed by this plasma polishing process. So now actually we are going to I'm going to actually present my work. So it is a uh, work actually, this thesis work by one of my PhD student. His name is actually Atul Singh Rajput, and one more actually this co-supervisor was there, Dr. Sajan Kapil. So along with this Sajan Kapil, actually we guided him, and then this is the work actually he has done. So this is the work actually, this post-processing of additively manufacturing biomedical implants. Uh, so this is the outline of my presentation. So Dr. Taylor, is my presentation is visible? Is my presentation is visible? So I cannot hear you.
Yes. Am I audible, sir?
Now it is audible now.
Okay. Sir, still it is not visible.
Is it visible now?
No, sir.
Oh. Okay, I shall share it again then. share the entire screen.
Yes, sir. Now it is visible.
It is visible now?
Yes, sir. Yes, sir.
Okay, okay, thank you. Okay, so thank you, Professor Taylor, for inviting me for this AICTE-ATA Faculty Development Program on recent developments in micro nano machining in context of Industry 4. So I will be talking about this actually post-processing of additively manufacturing biomedical implants. So this is actually one of our PhD student, jointly supervised by another faculty member, Dr. Sajan Kapil, and Dr. Atul Singh Rajput is the actually was the PhD scholar then. So now he joined as an assistant professor at NIT Surat. So I am presenting his thesis work and few works by other PhD students also. I shall present whatever we are doing in our lab nowadays. Okay, so first actually this some objectives actually we shall discuss why you are doing this kind of work. So we have developed one hybrid electrochemical magnetorheological finishing experimental setup. So it is a combination of two process. One is electrochemical process, another one is the actually magnetorheological finishing process. So that's why it is a hybrid process. So this setup actually we have developed. So we shall discuss later actually why we have developed actually this hybrid process. Why not only electrochemical machining, while not only magnetorheological finishing. Okay. So here actually this combined advantage of both the processes actually we have utilized here in this HSCMR process. So some analytical model actually we have used actually to some analytical model actually we have developed to predict the surface roughness and also to fabricate that actually this electromagnet. We need actually some analytical models, also some simulation model, so that actually we can get the right dimension of or diameter of this actually this electromagnet core material as well as electromagnet wiring. Okay, so uh, after that actually this surface enhancement of SLM fabricated femoral head. Okay, so by chemical etching, then surface profiling, and then feature-based hybrid MRI polishing system. So what are the limitations? And then surface enhancement by bone plate. And after that, actually this whatever this polished surface of that biomedical implants, we have done actually some corrosion test, wear test, and wearability test also. And we shall discuss that actually how we have developed this DAD based directed energy deposition based additive manufacturing system. And then some case studies we shall discuss and then conclusions. So these biomedical implants, you know that actually there are so many biomedical implants which are used in our body. So like this, actually this is the knee implant is there. So this is the knee implant you can see. So here this tibia part and femoral part, and in between this tibia and femoral there is a pad is actually there. So one pad is actually used, ultra molecular wave. So this pad. Now here actually this is the part which is actually in touch with this actually this femoral component. Okay, so every time it is actually there is a friction. So because of this actually relative motion between this actually this tibia and femoral component. So because of this relative motion, so whenever actually there is a part means in old age you see that actually so these bones basically actually they become close. So in that case actually there is a chances of actual arthritis. So what happens actually these bones actually touch with each other, and after some time actually you have to replace this actually this knee with some implant. So unless actually this implant actually it is made by uh, it is made its surface it is made highly polished or mirror finish surface, then what happens actually because of this friction in between these two bones, what happens actually, they touch with each other, and then it makes huge amount of pain to the person who has been actually operated. Also, because of this relative motion, also what happens actually, some debris particles also forms in between this actually this knee implant and then this femoral part. So these debris particles also it uh, uh, magnify that actually this more scratches on the surface. So that's why the surface roughness of this actually this knee implant should be in the nanometer range. Okay, so that actually to reduce the wear and tear in between these two bodies which are actually in relative movement between them. So other implants like actually this kind of hip implant, you can see that the same. So here actually this socket joint is there. So this kind of actually hemispherical socket which is inserted here inside the bone. And sometimes actually this kind of bone plates actually after fracture of this femur or any other bone, this kind of bone plates actually which is actually replaced in our body. Okay, so like that actually other implants like actually these dental implants also there. And uh, so these are the different implants which actually in our body we it is used. So here actually we shall discuss about this actually this hip implant, whatever this hip implant is there. Okay, so this ball actually we have made by additive manufacturing process. So these implants, why we have used actually this additive manufacturing, because of this individualization. Like these are the implants which are actually imported from outside. Okay, so it is based on whatever these imported components are there. So it is based on this actually average height and of that country. Okay, so everywhere actually there is a so there is a change in dimension of this actually implant. So so there is a need of actually customization of this implant or individualization of this implant based on means whoever actually been operated. Like if it is actually very small kit, so in that case, if it is actually operated using some biomedical implant, in that case, what happens actually, we first take the pictures of the existing one. Okay, so then from there itself actually we make the customized implant, and then it is made by actually this additive manufacturing process. So after making this using this additive manufacturing process, so after that actually it is a very complex. It is made of actually very complex geometry. So like this in knee implant, you can see that actually it is very complex in shape. So many actually this surfaces actually it is stitched or matched together. So making this kind of implant is not easy actually. So conventional machining process, it is very difficult to make this kind of implants. Okay, although it is made, it takes lots of time. So we can use actually additive manufacturing process or 3D printer, which is available nowadays. So using metal 3D printer based on actually customization of the patient. So after that, actually this implant actually it has to be functional integration. So functional integration means uh, it should not be actually this loosening. Okay, so like this one, like this hip implant, this portion actually it is inserted inside the actually bone. Okay, so if there is a wear and tear, if it is loosely fitted there, okay, so or over time if there is a actually this chemical reactions there with the body fluid, so in that case what happens, there is a loosening of this implant. So in that case actually we have to again operate on the patient, so which is very painful and very costly affairs also. So these are the things actually why we have considered this additive manufacturing process. Now after fabricating this kind of implants or any implants, all those implants, okay, so these implants actually has to be polished. So as I told that actually if it is not mirror finished, so wherever this actually it is touching to the uh, another component of the body, then there is a chances of actually more rubbing into the surface if some undulations are there on that implants. Okay, so But in case of actually this dental implant, actually we don't need any polishing there. So not in the nanometer range, but maybe in the micron range also it is fine. Okay, because there is no in dental implant there is no relative movement between these components. But for hip implant and knee implant, there is a relative movement between these components. So what happens actually if so there is a, you can see that actually this is the X-ray of hip implant here. Okay, so if it is not polished properly, so you can see that actually this hip implant, it is kept inside a acicular cup. Okay, so inside that acicular cup, actually it is kept inside. Okay, so if there is a relative movement is there in between this actually this uh, hip implant and then acicular cup, so then actually this kind of debris particles are actually generated. So these debris particles, it circulate with the body, and then our body actually thinks of actually some foreign particles. So then actually it releases cytokines, and then what happens actually our body actually reacts with this actually this kind of actually body implant, and then there is a wear and tear. So there is a chemical reaction with this actually this implant, and then there is a loosening of this actually implant occurs. So also if these debris particles also generated, it can affect our other organs like liver, kidney, brain, and heart. So that's why actually this whatever this implants which is actually manufactured. So wherever this relative movement is there, there we need mirror finish surface. Okay, so that's why actually we have developed this hybrid electrical magnetorheological finishing process. What we have seen that actually using only magnetorheological finishing process, it takes actually lots of time for polishing. Okay, so 7 to 8 hours time is required for polishing one implant. So what we have seen that using electrochemical assisted magnetorheological finishing process, so that time actually can be reduced to less than 1 hour. So first of all, actually, we shall discuss about this magnetorheological finishing process. You can see that actually this magnetorheological polishing fluid, it is a combination of these ferromagnetic particles, and there is a base media which is called, which is actually all either silicon oil or DNS water. So this magnetorheological fluid, it contains, as I told, actually ferromagnetic particles, and then it is mixed with actually also abrasive particles. So because of these ferromagnetic particles in that actual magnetological fluid under a magnetic field, you can see that actually this carbon ion particles or ferromagnetic particles, it forms actually chain, this kind of chain like structures. And when some abrasive particles are actually added with this actually magnetological fluid, so these abrasive particles are actually held in between this chain structure of this. These abrasive particles are actually held in between this chain structure of the ferromagnetic particles. Okay, so in that case, you can see that actually this so it become actually very strong fluid. So it behaves like a solid kind of structure. Okay, so like in actually in grinding wheel, you know that actually this grinding wheel, these abrasive particles are glued. Some adhesives are actually used to bond for bonding purpose of this actually abrasive particles. But in grinding wheel, there is a um, these abrasive particles, there is a certain path is there. So that is a constant path. But in this case, actually, this magnetological fluid, it is a smart fluid. In this fluid, actually, it takes the shape of the workpiece surface, and these magnetic particles actually takes care of the actually this bonding between these abrasive particles. So this magnetic field, it helps uh, the abrasive particles together. When this amorphous fluid passes through some workpiece surface, so it removes the surface undulations by the abrasive particles only. But carbon and iron particles or iron particles, it does not take part into the material removal, because these are actually these soft iron particles. So only abrasive particles actually take part into the material removal. So this amorphous fluid, it consists of ferromagnetic particle, abrasive particles, and some stabilizer and carrier fluid. which is called actually this base media. Basically, it is either silicon oil, mineral oil, or you can use actually this water-based media. So water-based media is used when you are using actually this glass, quartz, this kind of materials where water actually reacts with the this kind of this glass and quartz. But in case of actually this components, which is actually this, there is a chances of rusting. So in that case, actually oil-based media is used. Okay. So some stabilizer is used like oleic acid or glycerol, so that these abrasive particles, so its density actually very higher than this actually water. Okay. So in that case, if you keep this amorphous inside a container, so there is a chances that iron particles will actually, because of this higher density, it will come to the bottom of the surface of this container. Okay, so that's why we need basically some stabilizer, so which actually do not allow the iron particles to agglomerate. So if they agglomerate, whenever you are applying certain magnet, means some external magnetic field, so these iron particles will form chains. Okay, so under whenever you remove this actually this magnetic field, they will immediately demagnetize. So that's why we are using actually this carbon and iron particles. So its remnant magnetization is very, very less. So this means after removal of this magnetic field, so it will actually demagnetize immediately. But still small amount of actually this magnetic field, which is actually remnant magnetization, remains there in that actually this iron particle. So that's why actually it may actually agglomerate. Okay, so to avoid this agglomeration, we use some stabilizer there. Okay, so like oleic acid and glycerol, it makes an actually layer on the carbon and iron particles, and it does not allow to combine these iron particles together. Okay, so the similar fluid, there is a less sedimentation, optimal yield stress. So it's low viscosity, resistance for corrosion, and optimal concentration of constituents is required actually. So we have to optimize the components of this actually this methodological polishing fluid, so that it can be used for nano finishing process. So you can see that actually this is the magnet, permanent magnet. Here it is shown. So that is a perspex sheet. Here it is kept just above that, and now we are keeping some amount fluid over there. So immediately after application of this magnetic field, so whenever this iron particles or amount fluid comes into contact under some magnetic field, you can see that this kind of chains are actually formed. So you can see that actually this uh, so this amorphous fluid, whenever we are considering this Newtonian fluid, okay, suppose water, in this Newtonian fluid actually there is no stress, yield stress of this fluid. So it passes through this actually origin. But this amorphous fluid actually under magnetic field, it behaves like a non-Newtonian fluid, and it has certain yield stress. So this yield stress is here, it is shown tau 0. Okay, so whenever this amorphous fluid actually amorphous fluid, suppose it is passing through a cylinder. Okay, so under magnetic field it generates some kind of yield stress. Whenever this applied pressure gradient inside that cylinder is greater than this actual yield stress of this fluid, then only this fluid actually flows over the surface of the workpiece. So you can see here there is actually this amorphous fluid without any magnetic field, this amorphous fluid, and whenever we are applying certain magnetic field, it forms this kind of chain-like structure. It behaves like a solid kind of thing, and that's why this yield stress actually generated. Whenever applied stress is greater than this yield stress of this fluid, then this fluid, amorphous polishing fluid, can flow. Okay, so so this means actually this amorphous fluid under magnetic field, it behaves like a non-Newtonian fluid. So that's why it helps in actually this polishing purpose. So so you can see that actually this our this component, actually this biomedical implant. So these are actually mostly titanium alloy basically. So Ti6Al4V. So this titanium alloy actually we have considered for this polishing purpose. Because actually this titanium alloy, this grade 5 of titanium alloy, so the Ti6Al4V. So it is used mostly actually this biomedical implants. Okay. So under chemical reaction, you can see that actually here uh, what we have used actually this for hybrid electrochemical magnetological finishing. So this is the composition of the semi-fluid here. Carbon and iron particles we have considered 40% by volume, and we have used actually diamond abrasive particles 7% by volume, and then magnesium chloride 16.35% by volume, and ethylene glycol 6.15%, and then water, and then glycerol. Okay. So what happens actually this magnesium chloride and ethylene glycol actually it reacts with the titanium, okay, inside that actually this titanium alloy. So this magnesium chloride here, you can see what this chlorine, it releases the chlorine, and then it reacts with this actually this titanium, it forms actually titanium chloride. So this titanium chloride again actually under deionized water environment, okay, so it becomes actually this titanium oxide. Okay. Okay. So then this titanium chloride also it reacts with actually this ethylene glycol here. Okay. So it also again makes actually this so this titanium so this complex actual compound it generate, and then again it reacts with the water, and then it makes actually titanium oxide. So this basically this uh, under chemical reactions, you can see that actually there is an oxide layer actually formed. So initially on the workpiece surface, you can see that actually this oxide layer, whatever on the initial titanium of grade 5, whatever we have got here. So in that actually this uh, workpiece, so this titanium, this oxide layer formation, it is not actually uniform. Okay. And also this layer is very thin. Then after machining using this electrochemical machining, okay, so what happens actually this titanium oxide, this oxide layers, it removes that oxide layer, and then after reactions actually what happens, it again generate actually this titanium oxide. So there is a uniform formation of this titanium oxide which is generated on the workpiece surface. Okay. So we need actually this uniform formation of this oxide layer on the titanium workpiece. So it has actually lots of biomedical uh, mm, uh, characterization. Okay, so mostly actually whatever this metals which is used, actually biomedical implants which is used. So we expect that actually this titanium oxide uniform layer should be generated on the workpiece surface. So after that, actually, we need this electromagnet design. Okay, so this electromagnet, this is the core material here, and this is the coil here. Okay, so we have used actually very low carbon steel. Okay, so of 19 SWG and number of turns of this actually coil inside. Okay, so it is 5472. So these many turns we have used. Outside, actually, we kept one copper tube. So this copper tube is used actually to flow the actually chilled water inside that actually this copper tube, so that it can reduce the heat, whatever this heat is generated in that electromagnet core material, it can be released. Because this electromagnet, you know that actually this while you are using actually DC current inside that actually this electromagnet, what happens actually it generates huge amount of actually heat inside that coil or wire. So if this heat is not actually controlled properly, then it reaches that actually temperature as high as possible actually. So it removes the actually some layer on that copper wire. Okay, so some uh, mm, uh, insulator coating is there on that actually wire. So that layer actually it is removed. So that's why actually we need to have certain amount of actually this cooling system so that its temperature can be reduced. So this relative permeability of this low carbon core material, it is around 10,000, and this the composition, you can see that actually its carbon percent is 0.002%. Okay. So you can see that actually this MH curve. So you know that actually one vibrator sample magnetometer is there. Okay, so in that vibrator sample magnetometer, you can keep one small component, maybe 5 gram or 10 gram, okay, of that actually material, and then under a huge magnetic field, it generates actually this image curve in vibrator sample magnetometer. So this hysteresis loop actually this hysteresis loop basically actually you can see from there itself. Okay, so you can see that actually for pure mild steel, so this saturation magnetization is less than this pure iron core material. So here actually it is very higher than this mild steel. So it helps in actually generating more relative permeability of this core material. Now, so that is a requirement of this actually what should be the diameter of this actually core material, and what should be the diameter of this actually coil, what should be the diameter of internal diameter of this coil, and or core external diameter of this core material, what should be the shape of this tool actually. So for that actually we have used actually console, and we have solved this Gauss equation. Okay, so uh, after solving actually we have found that actually this dimension of this actually coil, dimension of this tool basically we have uh, we have actually developed. So that fabrication actually we have done using ANSYS. So you can see that actually without any mu metal, just below this actually this tool uh, or core material, we have used actually some mu metal we have used. So with the use of this actually mu metal, we can restrict the magnetic field to a small area. Okay. So so you can see that actually using this actually mu metal, you can see that actually more uniform shape of the coil or polishing tool using MR fluid is generated. And also in between this mu metal and this core material, we have used actually one uh, a non-magnetic material. Okay, one perspex sheet actually we have kept in between this core material and then mu metal. Okay, so without that actually we have found that actually so this magnetic field was not concentrated, actually it was spreading outside. So when we have used actually some non-magnetic material in between this core and then this tool, so this magnetic field was actually concentrated at that time. So this is the setup actually we have developed here. You can see that this is the 5-axis CNC milling machine. So this is the vertical center here. So instead of using actually milling tool, vertical milling tool, we have used actually this. We have fixed this electromagnet core along with this core material there. So here actually there are two rotation is there. So this XY table, it can move in the X direction, also it can move in the Y direction, and it has movement in the Z direction also. And also this table can rotate about Y axis, and also this table. So this here this workpiece also along with this table, it can rotate about the Z axis. Okay, so so this A and B axis movement is also there basically. So you can see that actually here how this MR fluid is generated. You have to keep this actually workpiece just below this polishing tool. So this polishing tool actually it is generated using a using actually magnetoroyological polishing fluid. So entire this core material actually it is rotated using this kind of belt drive, and one stepper motor actually we have used there. to rotate this build, and like that actually. So this core material also it is rotated. So there are so many movements actually we have given. This tool is rotating about this axis, and it can move in X, Y, and in the Z direction also. And also at the same time we have done actually this ECM process, electromagnetic electrochemical process, as well as magnetogeological finishing process. So in ECM process actually it polishes, it removes the material with a very high rate, and also using this magnetogeological finishing process, whatever this soft material generated by this ECM process or oxide layer which is generated by ECM process can be polished very easily. So that's why two power supply we have used. One power supply we have used for this DC power supply, we have used actually for this electromagnet, and another power supply we have used for electrochemical machining process. So after that actually we have done experiments to see that actually effect of applied current on the surface roughness. We have found that actually a 2 ampere current electromagnetic or electrochemical polishing process was actually this efficiency was very high, or percent reduction in RA. So this is means initial RA minus RA divided by initial RA minus final RA divided by initial RA. So like that actually percent reduction in RA is calculated. We have found that at 2 ampere applied current, electrochemical process was actually very good. Okay, so in that case actually we got actually very good surface finish. Also, this whatever this volume percent of electrolyte in AMR fluid we have checked. So we have found that at 45% of electrolyte volume percent, we got actually very good finishing. Okay, also rotational speed of the polishing tool, also it is important. We have found that at 800 RPM, we got actually higher value of percentage reduction in RA. And also finishing time, we have seen that actually it is drastically reduced. Here you can see that actually it is at 30 minutes, we got very good surface finish. And if you still do the polishing beyond that actually 30 minutes, we can see that actually there are so many scratch marks which is actually generated on the workpiece surface, which is not required. Okay, so there is a comparison between using magnetic field assisted finishing and also this hybrid electrochemical magnetogeological finishing. So we can see that using hybrid magnetic abrasive finishing process, this percentage reduction in RA with finishing time is less, but with the help of this hybrid ECM plus magnetogeological finishing process, we can see that percentage reduction in RA very high. Okay, so here you can see that actually using this magnetic field assisted finishing process. Okay, so it is not giving actually this mid finish surface. Say one pencil is kept just in front of the actually workpiece. Okay, so you can see that actually there is a reflected image of this actually pencil on the machine surface or polished surface. You can see here. Okay, so this blue one actually initial surface roughness profile. Okay, and then this is the red one, which is actually final surface roughness profile. Okay, so initial RA was actually around 325 nanometer, and then final RA we have achieved 12.90 nanometer on the workpiece surface. So you can see that actually this we have from the XPS result, you can see that. So before polishing, actually this this oxide layer thickness is very less, and after polishing, this oxide layer thickness actually it is increased here. Okay, so you can see that actually whatever this oxide layer before polishing it is 8 millimeter, and after polishing it has become actually 78 nanometer. So using this ECMR process, actually this oxide layer formation is increased. So after that, actually we have done, after some preliminary experiment, okay, we have directly started experiments on the femoral head. So this femoral head, you can see that here it is the CAT model of this femoral head. After that, it is then slicing operation has been carried out, because you know that actually this Because of this, this is actually we have told that it should be customized properly. So for customization, actually we have adopted this additive manufacturing process or metal additive manufacturing process. So these are slicing, actually basically this layer by layer we have to develop this actual component. So we have used actually powder bed fusion process. You know that actually powder bed fusion process. So that is a scraper. So this scraper, it gives a small thickness of layer of this titanium alloy on the surface on the table bed. Then after that, this first layer actually, or after slicing, whatever this first layer is there, it is actually generated on the table bed. And then another layer of this powder is actually deposited on the same surface. Okay, so that is a laser actually which is used for sintering purpose, for heating and then further sintering purpose, sintering of this actually this titanium alloy powder. Then after solidification, it becomes that actually this components is actually generated. So it is a layer by layer process. You can see that actually this first layer which is generated, then it is the second layer. Again, this laser beam actually falls over the surface wherever you need actually deposition. So this laser beam basically detects based on actually this CAD model. So basically we give the path on the slicing. So accordingly actually this laser beam falls on the surface. So we have a diode laser. It passes through actually fiber. So we call it actually this fiber laser. Okay, so it has a 400-watt fiber laser. We have used actually for developing this kind of mm, components, basically additive manufacturing components. Now in this component, we can see that actually this fabricated components, lots of undulations are there. As I told, it needs actually this lots of polishing actually required. So without that, actually this kind of debris particles are actually generated. So this debris has to be removed from that. So for doing so, actually first we go for this actually chemical etching. Unless we go for this chemical etching actually, so this ECM or hybrid electrochemical magnetological finishing process cannot be useful. So that's why actually first we have done this chemical etching process. Using chemical etching, we have reduced that initial surface roughness from the uh, macro domain to micron size in the micron domain. So after chemical etching, this is the surface, and after that we went for actually this hybrid electrochemical magnetological finishing process. Okay, so after hybrid electrochemical magnetological finishing process, you can see that this kind of uh, highly polished surface which is actually generated here. Okay, so why we need actually this polishing? So you can see that there are loosely bonded powders. Okay, so whenever actually this layer by layer we are generating here, so some loosely bonded powders, actually this raw powder particle adhere to the surface of the component. Okay, partially melted powders, so powder, some portion may be melted, some portion is not melted. So heat diffuses from the molten pool leads to the melting of the powder particles or the ceramic part partially. Boiling melts spherical entities separated from the melted zone. So this is called actually boiling effect. And semi-oil. So insufficient melting of the metal. So so there is no basically joining of this actually these powders. Okay, so one portion may be welded, another portion may not be welded. Actually, some semi-welded powders are also visible. So this kind of boiling effect you can see here. Okay, so these are the different defects which are actually visible on the surface of the additively manufactured components. Okay, so that's why actually we need to do this polishing business. So first of all, actually we have done this chemical etching using hydrofluoric acid and nitric acid basically. So this titanium, it reacts with this actual hydrofluoric acid. Okay, and also it reacts with the nitric acid also. You can see that after that it makes actual titanium oxide on the surface of the components. So this chemical etching we have done on a beaker basically. So outside one actually we kept some ice cube basically. This ice cube actually, because it is an exothermic process, it reacts, during reaction it generates lots of heat. Unless we reduce the or maintain the heat, actually what happens, so this reaction will not be perfect. Okay, so that's why we have used some ice cube there to maintain the heat. Okay, so after chemical etching, we can see that clearly it can be visible. So this is before etching and after. So this is actually after etching. So you can see that actually this from before etching, actually chemical etching, it was 14 micron around. After that, it reduced to 0.54 micron. Okay, here also we have tested actually what should be the concentration of this hydrofluoric acid and what should be the actual polishing time. You can see that at 20 minutes polishing time, percentage reduction in array, it is better. Okay, also at 3 molecular weight 3m concentration of this hydrofluoric acid, percentage reduction in array was actually good. So after chemical reaction, you can see that. So this is the initial surface. So this is the 2D contour profile of this initial surface. So this is the AFM image of that initial surface. So initially it was actually 14.89 micron. So after polishing actually or chemical etching, you can see that it is reduced to here 0.98 micron here. So here you can see it is almost polished here. It is the 2D surface contour plot, and this is the SMM image of the surface contour. So whatever these undulations are there, okay, so it is reduced here. So these are the atomic force microscope images of the components. Now we can see that actually this is the fixture here. One fixture is actually generated or fabricated to fix the workpiece vertically. Okay, so vertically upward, it is femoral implant. Okay, so whatever hole is there in that implant, it is inserted into the actually perspex fixture. And this is the tool here actually, just below the tool, this polishing fluid or magnetological polishing fluid is kept. Okay, so here actually most important thing, electrochemical machining and magnetological finishing, both the things actually occurs here. So you can see this actually in this video, how this finishing process occurs. So you can see that actually this the tool actually it is rotated about its axis, but entire surface of the tool actually has to be polished. So we call it actually this uniform polishing. So you can see that over time. So you can see that actually this how this actually tool or this tool how actually it is polishing the entire surface of the workpiece using this hybrid electrochemical magnetological finishing process. Okay. So so this advantage is that actually this tool, you can see that actually it rotates about this axis, okay, around A axis, and then it also rotates about the B axis also. So like that entire component, entire surface of the workpiece can be polished. Here you can see that actually this workpiece is actually this femoral hip implant actually it is kept fixed. Now tool, how this tool actually moving over the surface. Okay, so same thing actually it is done by fixing the tool. Only this up and down motion is there, but this workpiece actually it is rotated. Okay, so like that actually entire surface of the workpiece is polished. So after hybrid electrochemical magnetological finishing process, we can see that. So this is the after chemical etching, whatever surface we have received, and after that actually hybrid electrochemical machining process, electrochemical magnetological finishing process. So this kind of mirror finish surface actually we have achieved. Okay. So this is the SM image. There are still some kind of undulations are there, but after that actually you can see that on the same image after polishing. So this undulation is almost gone. Also, you can see that this blue one is the initial surface roughness profile, and this red one is the final surface roughness profile. Okay, of the same component before and after polishing. So after that, actually, we have checked whether there is a huge amount of heat, whether huge amount of heat is generated or not, because surface topography is very important. So whatever surface which is actually this implants, whatever surface it is actually generated, shape is generated, it should not disturb, okay, because of this heat generated during this polishing process. So you can see that as we have used actually this electrochemical machine process, we have to give the, so this is the negative terminal, it is used as the tool, and workpiece actually it is connected to the positive terminal. So here there is a spring loaded silver graphite uh, tool is actually which is attached to that actually this polishing tool for continuous supply of current. So what we have seen that actually this using surface topography study before and after hybrid electrochemical magnetology finishing, so it saves, does not degenerate basically. So this temperature variation is very, very less. Okay. So after that, actually, we have studied actually skewness and kurtosis. Okay, so these skewness and kurtosis, these are actually very, very important component in case of actually biomedical implants. Other than RA, so this gives actually huge amount of information. Whether there is a huge peaks are there, so if there is a huge peaks are there, then these biomedical implants, while relative motion, so these debris particles will be generated from there. So that's why uh, so we need actually basically these components should be generated like this kind of surface should be there. Okay, and there is a information like this number of peaks and number of valleys. Okay, so what kind of surface we have, so those are the information actually it will give in skewness. Okay, so here you can see that actually this in this skewness here, so more number of actually these valleys are there than here uh, more number of peaks. So here you can see more number of peaks are there basically than more number of valleys basically. Here you can see that in kurtosis, you can see that this kind of uniform surface will be generated. Okay, so which is expected, not like this kind of peak surface, which is not a bearing surface basically. Okay, so this kind of surface it will generate lots of actually this debris particle on the workpiece surface. Okay. So after that actually we have generated this bearing area curve. Okay, so before polishing and after polishing you can see that. So this is the actually this before hybrid electrochemical methodological finishing, and this is for after that electrochemical or hybrid electrochemical methodological finishing process. So you can see that actually for this skewness here 1.62 it reduced to actually 0.25. Okay, so SK, PK and VK, so these are the parameters. You can see that these are the values actually which is shown here. So these values almost actually it is reduced here in all the cases of bearing area curve. So after that actually we have tested actually this corrosion test, wear test. Coefficient of friction, we have seen that actually uh, this powder bed so this powder bed actually this additive manufacturing process, so this is the component here. So this coefficient of friction was more. After that edge surface it was slightly more, and after that actually this polished surface using hybrid electrochemical machine process, we can see that coefficient of friction it is reduced. Also we have rate it is drastically reduced from the polished surface. So these are the things actually which has been done using this wear test. Also we have done actually this corrosion test also. So this corrosion also you can reduce on the polished surface. You can see here this corrosion rate millimeter per year, it is reduced in case of this polished surface. Okay, so after that actually we have done weightability test to check whether this surface is actually this hydrophobic or hydrophilic. So there are lots of applications are there actually this kind of surface. In some surface actually this hydrophobic nature is required, in some surface hydrophilic nature is required. So uh, for biomedical implants. So after that actually we have done some feature based hybrid methodological finishing uh, system. So like that actually this we have shown that actually this bone plate So in that bone plate, actually, this suppose if there is some fracture of the bone, and then this kind of bone plates actually which is placed inside our body, so it supports the actually our bones, so that these bone parts can be healed over time. And then these bone plates actually this attached to the our bone using some screws, some joining devices are there. So that's why in that bone plate actually this kind of holes are actually generated. So using magnetological finishing process, you can see that actually this surface, you can see that MR fluid actually there is a accumulation of this MR fluid inside or tapped inside that actually holes. Okay. So this is not actually uh, expected basically. So what we did actually initially, we have filled with this kind of holes basically using some wax. So some molten wax actually is, we have measured actually how much volume is there. Okay. So it may be some complex holes also may be there. So it will, from this CAD surface, it will generate, it will calculate how much wax actually has to be filled up. Okay. So after that, actually, we do the magnetological finishing or hybrid electrical magnetological finishing process on the surface. Okay. So these are the holes actually, these are the surface which is actually made on a directed energy deposition based setup which overlap. Okay. So after that, after these components are actually fabricated by DD device, after that it has been done this milling operation. Okay. Okay, so on this milling operation, so some amount of surface undulations which is now uh, reduced. So after that, actually this this syringe basically there is a coil is there. Actually, this heating coil is there. Okay, using this heating coil through this syringe, actually we are depositing wax inside that actually these holes. Okay. So after filling this wax based on actual process parameters, okay. So after that we have done this hybrid electrochemical magnetological finishing process. Okay, so you can see that this kind of initial surface is the final surface. Okay, so bone plate. So this bone plate, you can see that first initially it this is the DD fabricated process, then it is milled. So after that, actually it is polished by hybrid electrochemical magnetological finishing process. So this is the initial surface. This is the surface after actually milling. So that's why so many scratch marks are there. After that, you can see that actually these scratch marks are almost removed. So these are the optical microscope image of this at a different stages of polishing. So so there is some underfilling and overfilling effect of this wax. Okay. So if it is underfilled, then this rest of the surface it is actually filled with MR fluid, and if it is actually overfilled, then this MR fluid actually this iron particles it mix it up with the wax there. So you can see that actually how we have developed this this kind of these bone plates here. So this is actually one kind of bone plate. So this is the another kind of actually bone plate which we have developed by DET process. So you can see that actually this is the laser source here, which is and there is a nozzle. Actually we have developed one gravity fed nozzle, and this is the laser source. So through this gravity fed nozzle, actually this uh, particles titanium alloy. So here actually we have used SS316L. So stainless steel particles which are coming through this nozzle, and then there is a laser source. This laser source actually it will fuse them, and there is a sintering process, and then these components actually it is generated. After that it is milled. Some milling operation has been carried out. After that actually this hybrid electrochemical magnetological finishing process has been conducted. So this kind of acid tubular cup, actually, we got it from some outside. Okay, we thought of actually doing polishing on this acid tubular cup. Okay, so but later we did not. The student actually left after that, and then we could not. So it is in our plan to make inner surface of this acid tubular cup, polishing of this inner surface. So you can see that actually this how powder bed process here, actually this laser source, so that is a scraper is there. Using this scraper, basically these are the components which are actually generated, and this laser source are used wherever this polish machining is required. So this kind of components you can see that actually which is generated. So this is the DET surface, DET process, as I told, that bone plates actually which are actually generated by this DET process in our lab. Okay, you can see that actually how it is developed basically. So this is the actually what we did. We have developed one DET setup here. So here this feedstock distributor. So it is coming. So generally actually this shielding gas is used, or some inert gas is used actually for flowing these particles, metal particles there, and through center actually one laser source is used, and like that actually this setup, this directed energy diffusion setup is generated or works. So in our case actually we have developed this nozzle. This nozzle basically it is a gravity fed nozzle is there. You can see that actually through this hole basically we are delivering this actually this fiber laser. Okay, and from this side actually this SS particles or any particles, metal powder for additive manufacturing, it falls. So this kind of actually this tidation it is generated. So it spreads the particles actually this uniformly over the surface, and then through this conical channel basically actually this particles actually falls, and then it generates actually uh, some focal point basically. Okay, so now what happens actually some there is a vibration actually it is generated here, you can see that. So that using vibration basically this whatever this clogging can be actually mitigated. So because actually this small channel here, so using this small channel there is a restriction of this actually these particles. Okay, so if we vibrate this one, so it can be that restriction can be recovered. So we can see here actually these metal powders. Uh, there are different kinds of actually this special particle distribution system. Okay, so ABC three types actually we are considered. So it should be uniformly uh, uh, uniform focal length should be there. Okay, so here actually laser source will follow on this focal length, and you can see that actually this kind of focal length which is actually generated. Initially it was actually 7 to 8 millimeter. Now we have reduced this one actually less than 3 millimeter here. Okay, so here actually through the center one laser source, fiber laser source fall, and it will do this actually this melting, and then uh, this droplet will fall on the surface wherever actually this we want to do the components. So these are components of this actually this gravity fed nozzle here. So this basically this nozzle along with this actually this laser optics we have attached to the our existing CNC milling machine here. Okay, so we have attached over there. So it acts actually this Z axis, or this the fiber optics, and also they are actually this gravity fed nozzle, both the things actually which is attached. It is little bit offset, and so that's why we have made program in such a way that this offset can be taken care of. So here this X, Y and Z axis movement can be given. And there is a fourth axis movement. So there is a chuck is there. It rotates with a maximum 6 RPM. We can rotate this chuck actually with a maximum 6 RPM rotation. And then this workpiece can be on a cylindrical surface also. We can, if you fix your workpiece over there on a cylindrical surface also, you can deposit. Okay. So this coolant on off that can be taken care of to take care of this actually this actual laser, when to fire, when not to fire, because we have actually this continuous source laser, continuous mode laser we are using. So using on off mode actually we are sometimes we are stopping, or sometimes we are actually firing this laser. So we can see here actually this working of this actually this DD. Here actually we can you can see that actually like 4 channels basically this through this cassette. So some 4 pipes actually we have attached over there, and through these 4 pipes actually we are depositing or flowing the actually this particles there. Okay. And through the center actually this, you can see that actually on a cylindrical surface how this deposition is going on. After deposition, using this actually tool, we remove undulations from the surface basically. So we have done actually finishing of knee implant also. This is my first initial student, Annesha Varman. She worked on this actual knee implant. So as I told, this is the femoral component and this is the tibial component. So in between this, actually this high molecular weight polyethylene component is there. Okay, so it is attached to this actually tibial component there. So this is the femoral component, which it is a very complex surface. So it needs to be polished in the nanometer scale. So this kind of tool actually we have developed. So this is the permanent magnet we have used, and this tool material actually we have used here is the mu metal basically. This mu metal, what happens? It restricts the magnetic fields of line into a small area. So you can see that actually this kind of magnetic lines of force which is generated here. Okay. So that actually the spherical kind of means tool surface can be generated. So this is basically iron particles or magnetological polishing fluid would be spreaded over there, and it will take this kind of spherical surface. So you can see that actually this is the tool here. Okay, so so at different places actually we have measured this magnetic field using a gauge meter, and we got a from simulation and experimental we have got the similar kind of deal. So after that, this tool basically it is attached to the milling center, the milling machine, CNC milling machine, and on using this tool actually we have used polishing on the surface. So here you can see that again this 4th axis of the CNC machine. So there is a chuck is there. It is at this workpiece is attached over there. So this is a tool which is kept over the surface, and every time this tool should be perpendicular to the workpiece surface. So this CNC program it is made in such a way that it is perpendicular every time it is perpendicular to the workpiece surface. Okay. So at a time we have polished the entire surface. Okay. So this is the final polished surface, and then initial surface it is made by 5-axis CNC milling machine. So on a titanium alloy basically of grade 5. So it has lots of undulations are there because lots of scratch marks are there by milling machine. So after that, after polishing, actually it got this kind of finished surface. So this is the experimental setup we first initially developed in our lab, magnetological average flow finishing process. For polishing this kind of miniature gears, you can see. So this is a fixture we have actually developed. So through this fixture, fluid passes through this actually gear, and then we have outside we have applied this magnetic field using this permanent magnet, and we do this actually polishing on the this kind of surface. So miniature gears. So So you can see that this kind of undulation scratch marks are there because these gears are actually generated by this wire cut EDM process. Okay, so because of this wire cut EDM, so there are scratch marks are there, also heat affected zone is there. So unless you polish this kind of surface, actually this mating of this gear is not good basically. So you can see that actually how polishing occurs. So through this fixture, actually this amount polishing fluid passes, and at the same time we have rotated also this magnetic field we have rotated from outside, and it passes through the workpiece and it does the finishing. So after finishing, you can see that at the different surfaces, top surface, involute surface, this face surface, it is polished. So, so what about this bars which is actually generated, okay, by wire ADM process? It is almost removed actually. So these are the work actually we are doing in our lab. So this is the magnetogeological abrasive flow finishing. So this is the plasma polishing process. So this kind of HRG shell actually which is used in ISRO. So we have a collaboration with the ISRO. One of the director who did PhD with me, and they supplied this kind of components there. So it is actually 20 millimeter diameter. This kind of HRG shell is there. So this thickness is actually only 2 millimeter thickness is there. They have made this kind of shell by using 5-axis CNC milling machine. Okay, vibration assisted 5-axis CNC milling machine. And then because this is a quartz, okay, so this quartz actually it is a brittle material. It's lots of cracks actually which is generated over the surface of this quartz. Okay, so these undulations has to be removed. Okay, so this kind of actual prism also they have made. So these cracks actually, if it is purely polished, so this kind of white marks should not be there. And if you follow, if you a laser source, actually immediately it will detect. So if it is highly polished, then it will not be absorbed there, this laser source. It will be passing through this quartz. And if some cracks are there, actually this laser source will be accumulated there. Okay, so it will be absorbed there. So this is the this setup. Okay, so inside that actually this helium and oxygen plasma, and then SF6 plasma also we have used later for polishing of this kind of components. So this is the setup actually which is magnetogeological finishing, which is used for polishing this kind of miniature. And this is actually this initial magnetogeological finishing setup we have developed in our lab. And this is the actually micro ECM setup. Also later now we have developed micro ADM setup, okay, in our lab. So these are the conclusions here. So thank you for your patience for listening. Okay, so if you have any questions, you can ask me now.
Okay, thank you, Dr. Manas Das sir. Now we are opening the session for questions, answer. If any question, participant can put the question in chat box or they can raise their hand.
Okay, so we have shown actually so many experimental setup. This kind of setup, some of the setup actually you can develop in your if you are in a private engineering college also, or any government engineering college, you can develop this kind of setup. So these are actually on some lathe machine or drilling machine or milling machine. Okay, so this magnetogeological finishing setup you can easily develop there. Okay, so only thing is that actually you have to ingeniously you have to make this actually magnetogeological polishing fluid. So it is also very cheap basically. So Loba Chemica is the company in India. Okay, so they supply these ferromagnetic particles. Okay, so one bottle it may be 550 or 600 rupees per 500 gram. Okay, so maybe 1000 rupees per kg. And this deionized water also there, abrasive particles also, this silicon carbide, it is also very cheap. Okay, so small amount of actually this polishing media you can use. So not huge amount of polishing media is not required. So on a lathe machine or drilling machine or milling machine also you can develop your setup, custom made setup, and you can do the this polishing operation, and you can publish your work. So I can still tell you that actually if you are using on magnetotechnological finishing process, there is a lots of chance of actually publishing in a very good journal. So Atul Singh Rajput, actually he worked in this magnetotechnological finishing, although he added this SCM process. Okay, so he published more than actually 20 research paper in his during 4 years of his actually this PhD. So still you can try.
Sir, I have one question.
Yeah.
How in case of the femoral head or any complex like knee joint, how we ensure the overall geometrical accuracy after the finishing?
Okay, so this actually
Because
magnetotechnological.
in the joint profile, three-dimensional profile, I think more important.
Exactly, three-dimensional profile is more important. So you can see that actually this magnetotechnological finishing, although it is a machining process, but it basically do the machining in the micron range. Whatever these particles, actually wear out particles which is generated there, it is in the actually very small nanometer or micrometer particles which is actually generated there. So it cannot change the shape basically. So that's why in additive manufacturing component, additively manufactured component, we have done this actual chemical etching, because initially those initial surface was around 15 micron. So now chemical etching, it is reduced to actually less than 1 micron. Then only if it is less than 0.5 micron, then only actually this magnetotechnological finishing process works. So there is a less chance of actually this geometrical shape change. So that's why we have done actually in one of the slide we have shown that actually this thermal image camera we have seen. Okay, we have shown the thermal image camera. From that actually we have checked whether actually this shape using this high speed camera also we have checked that whether there is a shape change is there. So there is no change in shape basically.
Okay, sir. Thank you very much, sir.
Thank you for inviting me.
Is there any other question from participant? So if there is no much questions, then we are ending our this session. So thank you, Dr. Manas Das, sir.
Thank you, Professor, for inviting me. So now I can leave now.
Yes, sir. Yes, sir.
Okay, okay, thank
Sure,
you.
sir.
Thank you.
Thank you very much, sir. Thank you.